repeat calculus on the topic of power series, the radius of convergence, and the interval of convergence. So it says for each power series find the center, the radius of convergence, and the interval of convergence. So on most of these, the ratio test tends to work best, but notice on this one, this is raised to the n power, it's actually the root test that would be better. And these power series, as opposed to regular series, the main difference is you've got variables in the terms, instead of all the terms just being constants. And in this case, our variable is x. And there's a little typo on the handout. So that, I think on the handout it's a 3 there, so just change that to a 5 on the numerator. It can still be solved with a 3, but it works out a little better with a 5. All right, so we're going to use the root test because this whole thing is raised to the n power. It tends to work a little more easily than the ratio test here. And then with the root test, you find the limit as n approaches infinity, just like the ratio test. But then what you do is you take this root, in this case the nth root of this whole expression, 5 over x squared plus 1 to the nth power. And what that does, the nth root cancels out the n exponent. Those are inverses of each other. So all we're left with is the limit as n approaches infinity of 5 over x squared plus 1. And then notice, normally you would substitute infinity for n, but there's no n's left once this exponent of n cancels out. So really, the limit is just going to equal this, because there's nothing to plug into for n. So we end up getting this expression here. 5 over x squared plus 1. And just like with the ratio test, though, in order to converge, because we're trying to find where it converges, this expression has to be less than 1. So this was a little different. Most of these end up being linear absolute value ones, but there's no absolute value with the root test. And also with the root, you can see this one's not linear. It's got an x squared in this case. So what we can do is to solve this, just first get rid of the fractions, multiply both sides of the inequality by the denominator x squared plus 1. So then we'll just be left with 5 is less than, well, if you distribute the 1, that's just x squared plus 1. And then rather than subtracting 1 and taking the square root of both sides, that doesn't work as well solving inequalities because of the plus or minus sign. The inequality sign can't go both directions, which it usually needs to go here. So instead, let's get one side equal to 0 by subtracting the 5. This works a little better getting one side equal to 0 for solving inequalities when they're not linear, when they're, in this case, quadratic here. So you can see you get x squared 1 minus 5 is 4. And then you can see that factors for the difference of perfect squares into x minus 2 and x plus 2. And so 2 and negative 2 make this exactly equal to 0. So the easiest way to solve this, to see where this inequality is true, is by putting them on the number line. Negative 2 and 2. Both of those make it exactly 0. And then when you test, notice, let's say you test negative 3. That makes this factor negative, this factor negative. Negative times negative is positive. You test 0. This is 0 minus 2 negative. 0 plus 2 positive. Negative times a positive is negative. And test 3. 3 minus 2 is positive. 3 plus 2 is positive. Positive times positive is positive. And what we're looking for is where 0 is less than this, or if you flip it around, where this is greater than 0. So we're looking for the positive interval. So this one is something a little where it happens. Usually, it ends up being converging in between two numbers here, hence the interval of convergence. But here, where this is true, is actually out here and out here. So there's actually two intervals. I guess this should be like parentheses. This doesn't happen very often, but in this case it is. So it actually converges when x is less than negative 2 or when x is greater than 2. And because it's not an interval with something in the middle, that means there isn't actually a center. So these go off to infinity and negative either direction, so there's no center. And without a center, there's also no radius of convergence like there usually is, because it'd have to usually be from the center to each of the endpoints. So a little weird case we got here. What we do still have is intervals of convergence, though. It's just there's two of them instead of the usual one. And what we still have to do, remember, just like the ratio test, this tells you when it converges when this is less than 1, it diverges when it's greater than 1, which would be right in the middle here is where it's diverging. But it doesn't tell you right when it equals 1, which 2 and negative 2 would make this exactly equal to 1. Whether it converges or diverges right there. That's the inconclusive part. So what you have to do, just like with the ratio test, take these endpoints of your interval one at a time and substitute them back into the original expression and see if it converges or diverges. And when you do that, then you can use any of those other tests we learned previously in the chapter, because then there won't be any variables in there. It'll just be a normal series with constants. So this is from n equals 1 to infinity. And let's substitute in the negative 2 first. So I'll have 5 over negative 2 for x squared plus 1. And then this whole thing is raised to the n. So before we use the, we're just going back to the original one before we did anything to this. But you can see that would just give you 5 over 5, that's just 1. So we have 1 to the n. Remember, 1 has a special property when it's a base. No matter what exponent we raise this to 0, that's 1, to the 7th, that's 1, to a fraction, that's 1, to a negative exponent, that's just 1 over it. So it's 1 no matter what the exponent is. There's no other number as a base like that where it's always going to equal the same thing. So this is actually equal to just the sum from n equals 1 to infinity of just 1. Now, there's different tests you can use here. You could, this is a geometric series. You keep getting multiplied by 1. Every term is 1. It's like 1 plus 1 plus 1 forever. One of the, probably the easiest test to use is the nth term test, or also called the divergence test. And all you have to do is find the limit as n approaches infinity. In this case, 1. There's nothing to plug into. It's just 1. And with the nth term test, remember, if this does not equal 0, which it does not, that tells you it diverges. If it was equal to 0, then that would just tell you that it might converge, and you'd have to use a different test. Or you could use the geometric series test and say, okay, well, the common ratio is 1, and that's not between negative 1 and 1, so it would diverge by the geometric series test also. That's another. Nth term is probably just a little easier. So when it diverges, that means you do not include it as part of your interval. So you don't put the equal or equal to there. But we also have to check it for positive 2. Sometimes you end up with the same for both of them, but not always. Sometimes they're different. So if we use positive 2, back into our original one. Normally you end up with a different series, but in this particular case, notice what happens. We get 1, because 2 squared is the same as negative 2 squared. So this ends up giving you the exact same thing as this one. And so we can use the nth term test again, and again it's going to diverge again, okay? Because of the same reasoning. So neither one has the equal to sign here. So your intervals of convergence, sometimes they can be written as inequalities, like this. Or the other way, in this case intervals of convergence, since there's 2 of them. In interval notation, you would write from negative infinity to negative 2, and then from 2 to infinity. You don't run into this case with more than one interval very often, but it can happen occasionally. All right, let's take a look at one more. And this one, though, even though these two look like good candidates for the root test, this one is not raised to the end, so because of that, let's use the ratio test. Like most of these, that tends to be the best test for most of these power series problems when you're trying to find the interval convergence and the radius convergence. So the ratio test, we still, just like the root test, find the limit as n approaches infinity. But unlike the root test, this has the absolute value. And then you first substitute an n plus 1 for all the n's. So we'll have negative 1 to the n plus 1. We'll have 2x plus 3 to the n plus 1 divided by n plus 1. And then it's divided by the original one, which is like multiplying by the reciprocal. So these two are the numerator, the n would go on the numerator here, and these two on the numerator would go to the denominator. And then we want to see if there's anything we can simplify there. N and n plus 1, those don't reduce at all. This would be like 6 and then 7, those would reduce. But you can see the 2x plus 3 to the n plus 1, 2x plus 3 to the n. You would just, when you're dividing with the same base, you subtract the exponents. So n plus 1 minus this exponent of n. The n's cancel out. And you're just left with 1. So now this is to the first. And you can also simplify the negative ones. Same idea. This is just going to be negative 1 to the first. However, really the negative ones, the part that makes it alternating here, when you're using the ratio test, you can, if you want to, pretty much ignore them. The reason why is because of the absolute value signs. The absolute value sign, this negative is always going to get canceled out anyway, so it's not really even necessary to put it in there because it's not going to matter at all. Every single time the absolute values are going to get rid of the negative. So let's see what we have left now. The limit as n approaches infinity. And then the absolute value signs, what they also won't affect is the n and n plus 1. Notice we're starting, this is another little typo here. We're starting at n equals 1. I think on yours it says 0 here. And 0 doesn't work because if you plug in 0, this first term would be undefined. So 1 for n and n plus 1, those are never going to be negative. So those are never going to be affected by the absolute value. So you can pull those on the outside, n divided by n plus 1. But then the part that could be affected, because we don't know what the value of x is this 2x plus 3. That's going to be the part that's still in the absolute value. And now it's just to the first power. And again, we're trying to find the interval of convergence where this converges. So just like the root test, this converges when this is less than 1. And well, first, actually, we can first simplify it first before we set it less than 1. By substituting infinity. Notice you get infinity here. The plus 1 is negligible, so over infinity. Absolute value of 2x plus 3. And you can see those completely cancel out, which often happens on these. Less than 1. And then to solve this, remember you rewrite to get rid of the absolute value signs. This means like the distance away from 0 is less than 1. So essentially it's between negative 1 and 1 on the number line. So you can rewrite it as a compound inequality. Negative 1 is less than what's inside the absolute value, 2x plus 3, which is less than 1. And then just get the x by itself in the middle here. There's 3 parts to this compound inequality. So whatever you do to one part, you have to do the other 2 parts as well. So when you subtract 3 here to get the x by itself, you have to subtract 3 here and subtract 3 here to keep it a true statement. So then we'll have negative 1 minus 3, negative 4 is less than 2x, which is less than negative 2. And then divide by 2. Now, if you had to divide by a negative number here, then you'd have to flip both inequality signs. But here we don't have to do that because we're only dividing by a positive 2. So we get negative 4 divided by 2. Negative 2 is less than Here the 2's reduced out x, which is less than negative 2 divided by 2 is negative 1. So let's draw that on the number line. So we have a pretty small interval here, just between negative 2 and negative 1. Is where it would converge, where this would be less than 1. So in this case, you can see the center is right smack in the middle. Really, to find the center, especially if you have weird values here for the endpoints, it's really just the average of these. In this case, you can see it's negative 1.5 or negative 3/2. So the center would be at x equals negative 3/2. And then the radius of convergence is from the center to either endpoint. Okay, just like with a circle, the radius is how far it is either way. That's the radius of convergence. In this case, you can see that would just be 1/2. And finally, here's our interval of convergence. But again, we don't know if it converges right at negative 2 or right at negative 1, because those are the places that make this exactly equal to 1. And the ratio test, just like the root test, is inconclusive there. So just like we did on the previous problem, we have to substitute these back into the original series one at a time, and then use any of those tests, or you can use any of them that we learned earlier in this chapter to see if the series converges or diverges at the endpoint. So let's start with negative 2. So we have the sum from n equals 1 to infinity, negative 1 to the n over n, and then we're going to plug in negative 2 for the x right there. And let's try to simplify this. So we can see what test would work best. So we have negative 1 to the n over n. This part is really over 1, so it really goes on the numerator along with the negative 1 to the n. So that's negative 4 plus 3. That's another negative 1 to the n. And then notice you have the same exponent, so you can really multiply the bases, but negative 1 times negative 1 is just 1. So this is the same as 1 to the n over n. But remember, we just talked about 1 to any power is always 1. So really, this just simplifies to the from n equals 1 to infinity of 1 over n. And in this case, this fits the p-series exactly, so let's use the p-series test. Remember, p is the, when it ends on the denominator like that, p is the exponent right there. So p equals 1. And with the p-series test, p-series test, if this is less than or equal to 1, then you know it diverges. It has to be greater than 1 in order to converge. So since it diverges, again, we're not going to add the equal to a negative 2. But let's try negative 1. Back in the original one. So I'll give you negative 1 to the n over n, and 2 times negative 1 plus 3 to the n. So when you simplify that, you get the sum from n equals 1 to infinity. Here we get negative 1 to the n. Negative 2 plus 3 is 1 to the n. But that's just 1. So that doesn't even affect anything. Just 1 to the n power is just 1. So on this one, notice we're still left with this negative 1 to the n. So if you plug in 1, it's going to be negative 2, it's going to be positive 3, it's going to be negative. So these are the easiest to identify what test to use. That's going to cause it to alternate. So we can use the alternating series test. And remember, there's 2 components to that. In the alternating series test, whatever is not part of the part that makes it alternate, we call that a sub n. And we first find the limit as n approaches infinity of that. substitute infinity, you get 1 over infinity, which is 0. Okay. So since it's 0, that means it might converge. If it was not 0, we'd know for sure it diverges. We could stop right there. Then the other thing you have to test is to see if the terms keep getting smaller, not including the negative part, just right here. So usually if you just find the first 3 terms, that's sufficient to figure that out. Here, if you substitute in 1 for n, the starting number, you get 1 over 1 is 1. When you substitute in 2, you get 1 over 2. When you substitute in 3, you get 1 over 3. So you can see the terms, the denominator keeps increasing by 1. So those do keep getting smaller forever. So both of those are true, so this one converges when x is exactly -1. And when it converges, then you add the or equal to. But it does converge. So sometimes they do the same thing, but in this case, at one endpoint it diverges, the other endpoint it converges. So that would be our interval of convergence. You can write it that way, or you can also write it in inequality notation. Interval of convergence. These are the x values that cause the series to converge. Is -2 with the parentheses, so -1 with a bracket. And that concludes the notes for AP Calculus on the topic of power series, finding the radius of convergence and the interval of convergence.